Today, we're diving into the fascinating world of logic gates, the building blocks of digital electronics. Logic gates are at the heart of digital systems, microcontrollers, computers, and pretty much every electronic device you use. By the end of this video, you'll understand exactly what logic gates are, how they work, and why they're so important in electronics and computing. In digital systems, the number 0 usually means low or off, while 1 means high or on, just like flipping a light switch in your house. Logic gates take these on and off signals and use them to perform simple operations based on Boolean algebra. Now, Boolean algebra is a branch of math that deals with only two values, true, 1, or false, 0. It defines rules for combining these values using logical operations like AND, or, and not. In short, Boolean algebra is the math of logic, the same math computers use to make decisions. Logic gates are simply the hardware version of Boolean algebra, making it possible to design everything from a basic calculator to a modern microprocessor. Let's start with the simplest gates using just switches. AND gate. Imagine two switches connected in series. The light bulb at the end will only turn on if both switches are closed. That's the AND operation. The output is high only when input A and input B are high. OR gate. Now connect the two switches in parallel. The bulb will light up if any of the switches is closed. That's the OR operation. The output is high if either A or B is high. So with just switches, you can visualize the foundation of digital circuits. Of course, in modern electronics, this switching is usually done with MOSFET transistors instead of mechanical switches. In Boolean algebra, a truth table is a chart that shows all possible input values and the corresponding output. It's the simplest way to see how a logic gate or circuit behaves. Here's a quick rundown of the main gates. NOT gate, or inverter, flips the input. If you put in a 1, it outputs 0. If you put in a 0, it outputs 1. AND gate, like the series switch, the output is 1 only when all inputs are 1. OR gate, like the parallel switches, the output is 1 when at least one input is 1. NAND gate, an AND gate with a little bubble at the output, which means not. It outputs 0 only when both inputs are 1. Otherwise, it's 1. NOR gate, an OR gate followed by a NOT. The output is 1 only when both inputs are 0. XOR gate, exclusive OR gate, outputs 1 when the inputs are different and 0 when they're the same. XNOR gate, the opposite of XOR, outputs 1 when the inputs are the same and 0 when they're different. These truth patterns define how digital systems make decisions at their most basic level. Logic gates can actually be built using different technologies, such as resistor-transistor logic, RTL, diode-transistor logic, DTL, transistor-transistor logic, TTL, CMOS logic, or complementary metal oxide semiconductor, ECL, or emitter-coupled logic, pass transistor logic, and more. But the most widely used today is CMOS logic. In CMOS, each gate is built with a mix of P-type and N-type MOSFET transistors. The beauty of CMOS is that it consumes very little power, especially when not switching states, while still allowing for high speed and high density. That's why modern microprocessors, memory chips, and almost all digital integrated circuits are based on CMOS technology. Now, among all the logic gates, there are two very special ones, NAND and NOR. They're called universal gates because you can build any other gate using just them. For example, by combining NAND gates in different ways, you can create AND, OR, and even NOT gates. The advantage here is that design and manufacturing become much simpler. Instead of making separate circuits for every single gate type, engineers can build entire systems using just NANDs or just NORs. This flexibility makes universal gates essential, not just in theory, but in real-world chip design. So, let's quickly recap. We started with Boolean algebra, saw simple switch models for AND and OR gates, explained all the major logic gates and their truth tables, looked at different logic gate technologies with a focus on CMOS, and finally highlighted the universal gates. Logic gates may look simple by themselves, but when you combine them, they form the backbone of all modern digital devices. If you found this video helpful, don't forget to like, subscribe, and share it with your friends. And stay tuned, because in the next video, I'll show you how we can use these logic gates to build more complex digital circuits, including memory units and adders. Thanks for watching, and I'll see you in the next one.